Now we're going to get to some probability rules. We're going to start with what's called the addition rule. But over here, I've got a table of values about who reads now this is people, who actually read newspapers and things, but, back in the day they did that. You got the New York Times, which is one newspaper, very well known, and the USA Today. That's a Y. That's an A. And they asked percentage of everybody they asked, do you read the New York Times or do you read the USA Today, or maybe some read both, and that's what this table represents. So the first thing we have to do now, this is what would be called a probability model. All right, the probability model here shows the results of what I asked questions about. So I got 5% of those who responded said they read both the the New York Times and USA Today. The question is, of those who were asked, who said neither New York Times nor USA Today? Well, to do that, a couple different ways you could go. I could say, well, first I'm going to add across. Okay, this is 25%. 25% of the people read the New York Times. All right, and then down here I got 40% of people, so I'm just adding, read USA Today. Well, 40% read USA Today. How many do not read USA Today? That would be 60%. That's complement rule. All right, same thing here. If 25% read the New York Times, that means 75% don't read the New York Times. And these should, both rows and columns, end up adding up to 100% if we're doing this, that is, as percents. So to do that, 35 to 75, that's 40. But then also 20 and 40 here also adds up to 60. It works both ways. So sometimes you'll be asked to finish finding those probabilities. You can do a table to do that. The addition rule is if I have two events, A and B, the probability of A or B, remember that union symbol is union. When I read it using the English language, I read it as the word or. Okay? So the probability of A or B is equal to the probability of A plus probability of B minus probability of A and B. That's intersection, probability of A and B. So again, that little symbol right there is and when we're using the English language. And mathematically, it's called the intersection symbol. Okay, the intersection symbol. So when we're doing this here, let's let A be those who, let's see. Let's let A represent those who read New York Times. And let's let B represent don't read the USA Today. And so now we're going to find these probabilities. So I start by saying, okay, those A is those who read the New York Times. So what is the probability of A? The probability of A is the probability of those who read the New York Times, which that's yes for New York Times. If I go all the way across, 25% of the people read the New York Times. What's the probability of B? B is those who don't read the USA Today. So I go to USA Today. No. How many people don't read the USA Today? And that's 60%. Now, in our last examples from the previous video, we said if they are disjoint, then we can just add them up. But sometimes we don't know if they're disjoint. So what we're going to do is we're going to continue on anyways and say, okay, well, then we're going to find the probability of B and A. All right, so A and B is those who read the New York Times and do not read the USA Today. So they read the New York Times and not USA Today. So where do those intersect? They cross paths right there. So the probability of A and B from my table is 20%. All right, to do this, I add the first two. and then subtract the last one because it's adding, then subtracting. So 85 minus 20 is 65%. That's how I use the formulas to do the addition. Now, it's possible that you could just look over here at this table and go, well, probability of A, those who say yes is here. And then USA Today, that's these people here. And if you add up those three parts, 5 and 20 and 40, you'll also get 65% either way. But what we're doing when we're doing this is the fact that when we did this first one, pick another color, go over the top. When I did this one and got those 25, and then I went down and did these, I counted that 20 twice. I counted it once with the 5, and then once with the here, and then I also counted it once when I counted the 40. So that's why I have to subtract it away one time. I can't add it both times, or I have too high of a probability. And that's how we use the addition rule. All right, now we're going to use this same table from the previous one. So just recall that the yes, no on the left and on the left over here is New York Times. Up here on the top is the USA Today. We're going to do what are called conditional probabilities. All right, a conditional, well, it's kind of like how it sounds. It'll be based on a condition to find out the probabilities. All right, and here's the formula for it. Probability of A, vertical line means given, B. So this symbol right there is a vertical line, it means given. All right, probability of A given B is equal to the probability of A and B divided by the probability of B. Now if I go back to my last example, A was those who said yes, this was A, this row, and those who said B, that was this column, no to the to the USA Today. So to find A given B, what I'm really saying is if I know B, that is given B, and all I'm going to consider is B. So when that happens, what I usually do is I'll go to my table. I'll be like, okay, given B, so now it's only this. Only those. Given B, what is the likelihood that A happens? So this is my new frame of reference. Only those. What is the likelihood of A happening? So what's the probability that they read the New York Times? Well, how many ways does it happen? It happens 20 ways. Out of how many? Out of a total of 60. So it's 20 over 60. But now let's use the formula to figure it out. Probability of A and B, which is this right here, 20% or 20 out of, remember how many the whole thing is out of? 20 out of 100. All right, so this is 20 out of 100, which is 20%, divided by the probability of B. B is the likelihood that they do not read the USA Today. That is 60 over 100. And when I reduce, I'm left with 20 over 60. That's called a conditional probability. When we're not working in percents, it becomes a little bit more, less obvious, put it that way. So making sure that you're really paying attention to given, again, what does given mean? Given means instead of out of everything, so instead of out of the total 100, the given means my new denominator is based on only that thing that I'm given, in this case, in the I do not read the USA Today column. All right, that's a conditional probability. A unique conditional probability is this. This is a unique one. If probability of A given B is the same as just the probability of A. So what if knowing B means that the probability of A is still the probability of A? So did knowing B change anything in terms of my probability? When the answer is no, if like, so, okay, so B has no influence, it did not change probability of A at all. If this is true, if that's true, then A is independent of B. That's a very important probability rule. All right, and you can do it either way around. It's a two-way if-then statement. So if we change this, if A is independent of B, then those probabilities are equal. All right, so independence means knowing B, so given B, knowing B, the likelihood of A does not change. Again, independence means knowing one event, B, does not change the likelihood of the other event, A, happening. That is what it means when we say two events are independent. What are examples of independent events? If I roll a dice and I get a 2, and I'm going to roll the dice again, does knowing that the first roll was a 2 change the likelihood that the second one will be a 2? Well, no, you can't warm up a dice. Flipping a coin, same thing. Knowing one event does not change the likelihood of another. Now with a deck of cards, there's two ways to do it. You can shuffle a deck, take out a card and look at it, put it back in, shuffle it up again, pick out another card. That's called with replacement, so you replaced it. And the other way is you shuffle a deck, and you take out a card, you look at it, you set it down. Then you shuffle what's left, you take another card and look at it. So my question to you for the reflection response is, in which case are they independent events? That is, knowing the first one does not change the likelihood of the second one happening. Put that in the reflection response. If you have to rewind this, hear independence again, think about it for a minute. But if the probability is the same, whether you know B or not, then it's independent. So which of the two, either with replacement or without replacement, are they independent events? The next video is going to be on the multiplication rule. So this is what's called the addition rule from the first part, and then the conditional probability rule. The next video is on the multiplication rule, which is really just the same thing as the conditional probability rule, expanded a little bit, and I'll write it down here quickly, and then we'll get to it in the next video. Probability of A and B is equal to probability of A times the probability of B given A. You see, it's pretty much the same thing as the independent rule. Just kind of manipulated some things around, but we'll get to that and how that works in the next video. Fill out the reflection response, ask me a good question, and we'll see you in class.